Welcome, everyone. Today, we are going to explore one of the most famous and fundamental concepts in all of geometry. But we are going to look at it through a slightly different historical lens. You most likely know it as the Pythagorean Theorem. But as we will see today, it also proudly bears the name the Baudhayana Pythagoras Theorem. To understand where this mathematical journey begins, we actually need to travel back in time to look at an ancient architectural puzzle. The year is 800 BCE, and we find ourselves in ancient India. The goal for our architects here is highly practical. They need to build a square fire altar that is exactly double the size of an existing one. The big question is, how exactly would you do it? If you're thinking what most people would think, your very first instinct might be to just multiply the sides by 2. Our first guess is usually based on simple intuition. Why not just double each side? But let's test that. If the original side is 1 unit, the area is 1 square unit. If we double that side to 2 units, the new area becomes 4 square units. By doubling the sides, we accidentally ended up with 4 times the area, not double. Clearly, standard arithmetic wasn't going to cut it for this construction. So, what was the actual solution? This is where we are introduced to Baudhayana's brilliant discovery, which was recorded in verse 1.9 of the Shulba Sutra. He figured out that drawing a square based on the diagonal of the original square produces an area that is exactly double. We can easily see the visual proof right here. The original square is made up of 2 identical triangles, while the square built on its diagonal is made up of exactly 4 of those same triangles. It's a perfect double. Now that we know how to double a square's area, what if we wanted to do the exact opposite and halve it? To get half the area, we simply reverse the process we just learned. By drawing a tilted square that perfectly connects the midpoints of the larger square's sides, you shrink the area in half. Notice how the large outer square contains 4 triangles, while the tilted inner square contains only 2. And just like before, remember that simply halving the side length would shrink the overall area to 1/4, not 1/2. This geometric trick works perfectly, but it brings up a fascinating mathematical problem regarding the exact length of that diagonal line. Let's look at the math. If our original square's sides are exactly 1 unit, the square built on the hypotenuse has an area of 2. Following the equation c squared equals 2, we find that the length of the diagonal c is the square root of 2. This gives us a length that lies somewhere between 1 and 2. But trying to write down the exact fraction for this number led ancient mathematicians to a startling realization. It turns out the square root of 2 is an impossible fraction. If we assume the square root of 2 can be written as a neat fraction like m over n, squaring both sides of that equation gives us 2n squared equals m squared. But here is the trick. Square numbers always have an even number of prime factors. The left side of our equation has an extra 2, meaning it has an odd number of factors, while the right side has an even number. This mathematical contradiction proves that the square root of 2 cannot be written as a fraction. It is fundamentally an irrational number. So the diagonal works beautifully for working with identical squares. But architects eventually faced much more complex problems. We just saw how to combine 2 identical squares into one by using the diagonal. But what if we need to combine 2 squares of completely different sizes into one single perfect square? Once again, Baudhayana had an incredibly elegant geometric trick up his sleeve to solve this. In verse 2.1, Baudhayana provides a stunning visual proof for this exact problem. He showed that the 2 different size squares can be carefully cut and rearranged perfectly into one brand new square. And where does this new square fit? It is built directly on the hypotenuse of the triangle formed by the other 2. This visual manipulation translates perfectly into one of the most famous and recognizable equations in all of mathematics. And here is that grand equation. A squared plus b squared equals c squared. Bodhayaна's theorem, recorded around 800 BCE, formally states that the area of the square on the hypotenuse equals the sum of the areas of the squares on the two sides. While this is widely known today as the Pythagorean theorem, named after Pythagoras around 500 BCE, Bodhayana was actually the first to state it in this general form. This elegant equation also opened the door to identifying special sets of numbers that make the math work perfectly. These special sets of whole numbers that fit a squared plus b squared equals c squared are known as Bodhayana triples or primitive triples. A few famous ones include the numbers 3, 4, 5 and 5, 12, 13. What's incredible is that if you take any triple and multiply all three numbers by any integer k, you create a brand new scaled triple. Because of the scaling rule, there are absolutely infinite combinations to discover. But how did ancient mathematicians figure out these specific number sets in the first place without modern calculators? They generated these triples using a clever trick involving odd squares. It turns out that the sum of consecutive odd numbers always creates a perfect square. For example, 1 plus 3 equals 2 squared. The trick is this. If the odd number you add is itself a perfect square, you automatically generate a triple. For instance, 9 is the fifth odd number. Because 9 is a perfect square, we get the equation 4 squared plus 3 squared equals 5 squared, giving us the classic 3, 4, 5 triple. This beautiful relationship involving squares fascinated mathematicians for centuries, eventually leading to one of the most famous challenges in history. In the 17th century, a mathematician named Pierre de Fermat pondered this exact concept. He wondered, we know this relationship works for squares, but what about cubes? Like a cubed plus b cubed equals c cubed. He famously claimed in a margin note that there are absolutely no whole number solutions for powers greater than 2. This claim, known as Fermat's last theorem, sparked a 300-year mystery marked by failed attempts from brilliant minds. It wasn't until 1994 that a mathematician named Andrew Wiles finally proved it at the age of 41. To wrap up today's lesson, let's bring this all back to ancient India to see how Bodhayana's grand equation was used to solve real-world riddles. This brings us to a beautiful geometric puzzle known as the lotus problem, written in 1150 CE in Bhaskaracharya's famous text, the Lilavati. The problem describes a lotus stem standing exactly 1 unit above the water's surface. When blown by the wind, the tip of the lotus touches the water exactly 3 units away from where it started. The question is, what is the exact depth of the lake? To solve this riddle, all we need to do is sketch out a blueprint and apply our favorite theorem. Let's build the triangle. The distance across the water is 3 units, and the depth of the water is our unknown variable x. The total length of the stem is the depth plus the part above the water, making our hypotenuse x plus 1. Applying Bodhayana's theorem, we set up the equation. 3 squared plus x squared equals the quantity x plus 1 squared. Expanding the right side gives us 9 plus x squared equals x squared plus 2x plus 1. Simplifying that leaves us with 8 equals 2x and dividing by 2 gives us x equals 4. The depth of the lake is exactly 4 units. And with that elegant solution, we can truly appreciate the incredible, enduring power of this ancient mathematics.